something just happened and you had a heart attack and time all ended, it will begin again.
All right. This is a good series. I'm glad you guys kept this going.
Yeah, I'm glad we kind of hung in there through the crazy beginning, and I think now people know about it. And
yeah.
If you come to all of them, you don't have to pay for PDHs.
Yeah, yeah. No, that's
Although
great.
They're very civil oriented overall, but
yeah.
In any case, usually other disciplines can still claim something.
Yeah. No, it's great. I mean, you know, and then the way that the state's making you keep track of all your education now.
Yeah.
Pays off.
Well, I went to a conference this week, and my final report from the conference came in 3 different unit types. I got PDHs, CEUs, and GHUs or something. And I'm like, I have to somehow convert CEUs to PDHs, and I don't even know what the GEUs are. They were you swiped in going into the vendor area, and you got time in the vendor area, but I don't does that count as this? I'm just gonna delete that one. I'm not gonna worry about that.
I actually got audited a couple of years ago.
You really?
I was surprised. I just thought I'd avoid that, you know.
Yeah. Greg Jones did a handful of years ago too, and it made him pick up the pace on how to keep track of things.
Yeah.
So.
Yeah. Yeah. So I keep better track of it now.
Yeah.
I had to kind of rebuild some stuff.
Well, and yeah, the better that you get a certificate or something, better off. Andy.
Hi, Vern. How are you? Good.
All right, I think we're going to get going. It's about 11:45. Thank you all for coming to yet again another College of Engineering seminar series. If you're seeking professional development credits, the password today is technology. Again, it's on the slide. No capitals, though. And I'll try to have a student who will be here at the end say it again. So today we have Matt Steffel from Steffel Engineering to talk about trenchless technologies. I think, Matt, you've given some adaptation about this when we were in the other venue.
That's correct.
And so I think it's a great talk, but I'm going to have to leave. So I will leave this to Matt, and I'll leave it to Hayden or possibly Patrick at the end to round it up. I'll remind Matt again at the end when you take questions, just repeat the question. And Matt, the floor is yours.
Very good. All right, so it's my pleasure to be here today to talk about a subject that is close to my heart, which is trenchless technology. And what I'm going to do today is I'll talk a little bit about the different parts of this part of the engineering world, and a little bit about how it's used here in Alaska. And trenchless technology has a lot of different facets. I'm not going to cover all of them today. It's almost impossible to do that within an hour. So I'll touch on the ones that that we see here in our state, or maybe we think might be here in the future. So trenchless technology, let me just explain what it is. It's basically it's a way to construct utilities by minimizing service disruption and also social costs, i.e. traffic control or public impacts, items like that. And it's kind of broken into 2 parts. One part is pipe renewal, and one part is pipe replacement. And you'll see that as we go through the topic today. And a little bit about the history of trenchless technology. It really kind of kicked off in the 70s when cured in place pipe and horizontal directional drilling were really, I want to say, invented and started to be used in the constructionist world. And there's a lot of trenchless work that happens in Alaska. And I've been in this business for 30 years and have really seen it grow. And I think the future in Alaska looks good. So I'm just going to go through a handful of different technologies. The first one's going to be slip lining. And this is an old traditional process. It basically is inserting a smaller pipe inside of a larger pipe. And the word slip lining is oftentimes confused with cured in place pipe. Slip lining is basically putting a rigid pipe inside of another pipe. And you can see in the photos here, the one on the left, they're slip lining a water main there. The blue pipe is a piece of PVC that's going inside of a piece of ductile iron pipe. The photo on the right is a slip lining project in Ketchikan, where a contractor was inserting an HDPE pipe inside of a ductile iron pipe force main. And the nice thing about slip lining is it can be done by general contractors. It doesn't require a lot of specialized equipment. You do lose capacity when you do this. Your pipe becomes smaller. And it's used for sewers, culverts, water mains, a lot of different varied utilities. And in terms of Alaska, slip lining has been done here for quite a while. The first slip lining job I heard about in Alaska was done in Fairbanks in the 80s. I think it was in the 80s, when they actually used ductile iron pipe to slip line some techite pipe that was failing structurally. So it's a renewal process that can be done by a lot of different, can be done by general contractors. These pictures here show another couple of more slip lining projects. The one in the upper right is a large diameter culvert underneath the runway, where they used a CMP pipe as a slip liner inside of an older CMP pipe that was corroding. And the one on the lower left is slip lining in a live flow condition. This is done a lot in the States. This picture is from actually some work that was done in Anchorage, and where they're able to maintain live flow while they're doing the insertion work. Cured in place pipe. This is probably the most popular rehabilitation method in the world in terms of the trenchless world. And this is really one of the technologies that kicked the trenchless industry off. When they were able to find a way to repair pipes in the ground without digging holes. Mostly used for sewer applications. It is being used for water applications now. And you're basically taking a felt tube that has resin impregnated in it. It's soft, inserting it inside of a hose pipe, and then using heat or light to kick the resin off, and it basically expands against the pipe wall and becomes a hard, basically just like a hard sock inside of the hose pipe. It takes specialized equipment in most cases. As an engineer, you're designing the wall thickness of this liner to fit the conditions. And it's also, it can be cured with hot water or steam. And then nowadays there's newer processes where they cure liners with light trains. And I'll have some pictures on the next slide that'll show that. So on this slide here, the picture in the upper left is a UV liner before installation. In the lower left, you've got the light bulbs that are used during UV liner the curing process. The photo in the upper right is the more traditional insertion process. We're using water to insert the cured in place liner inside of a sewer pipe. And then the picture on the lower right is another photograph of a UV liner being inserted into a sewer main up in Fairbanks. Again, this is the most popular trenchless technology in the world today. On to the next one. So water CIPP is a offshoot of cured in place pipe, and it's a technology that was developed, really came into its own like around the year 2000, and it's semi-trenchless. It does require some digging. You can see in the photograph in the lower right here where they have dug a pit to reach down to get down to the water main, cut the water main apart, and they're inserting a liner into it. This was actually a water main that was lined out at the Anchorage airport here. And of course, the picture in the other photo here shows a water liner inside of a water main, the end piece of it. They use epoxy resin in these liners for the most part. You can see in the lower bullet here some of the companies that are now doing it. You've got Aquapipe, Certex is a UV cure process. Nordipipe is a system that's used in Canada exclusively. And then RS Technique, which is one of the newer players in this game. This is a maturing industry. It really took off, like I said, about 18 or 20 years ago, and becoming more and more popular as time goes on. Anchorage actually has done quite a bit of water CIPP work, and early in the early years was one of the cities that did more of it than most other communities in the country. So,
yeah.
Yes.
What's the difference between CIPP and water CIPP? Thought I heard a differentiation there.
The question was the difference between water CIPP and regular CIPP. The word cured in place pipe is basically describes both methods, and this is just you're using CIPP pipe inside in cured or CIPP liners inside of sanitary sewers, storm pipes, and now they're doing them inside of water pipes. So they use the same term. Yeah. Another part of water CIPP work is the service reinstatement, and they can do this robotically without digging up the services. The picture on the right-hand side shows the robot kind of through the different steps that it goes through. And of course, the photo on the left is the robot itself. The driver observes it with a camera, positions it over the service, drills into the service and opens it back up with a drill tool. And I forgot to mention that they do the same thing in sewers too. When they do a CIPP liner inside of a sewer, they can reinstate the service with a robot from inside the pipe and do not have to dig a hole. So that's one of the beauties of that technology. Another technology that we see in the trenchless industry is fold and form. It's a process actually that the reason I bring it up is because it's kind of used in specific situations. It's a system that was used in Fairbanks quite a bit about 20 years ago. College Utilities bought the process and did quite a bit of fold and form work within their sewer system where they had like a global failure of some pipe there. Basically, you're taking a piece of PVC, heating it up, bending it, pushing it inside the hose pipe, and then expanding it. And then when it cools down, it stays in place and stays expanded against the hose pipe. U-Liner is one of the more popular fold and form companies. This process is used in sewers and culverts. They've had some issues over the years here and there with bonding or separation from the hose pipe and shrinkage. But anyways, it's still in use today. Another trenchless technology is the tight fitting liner. This is a little bit of it's not a real mainstream process. It's a pressure pipe application that's a little bit similar to fold and form, which is the one that we talked about just previously here. Sometimes it's called swage lining, and they basically take a piece of HDPE pipe and fold it or shrink it and make it smaller, and then pull it into a hose pipe, and then it goes back to its original shape over time. And it's depending on the thickness of the HDPE pipe that you're using here, it can either be a structural repair or a non-structural repair. And it's used a lot, around the world in transmission mains and gas lines, in pipelines where you don't have service connections. It has been used in Alaska. I heard from an engineer at BP a few years ago who told me that they had done some tight fitting liner work up on the North Slope. So it's a technology that you may never use, but it's out there. So spiral wound, another kind of a crazy technology used in our business. In this method, they actually take a thin piece of PVC pipe and they spiral wound it inside of the hose pipe, and as it's being sent down it locks in place with itself, and you're basically building a pipe inside of a pipe. It's used quite a bit in culverts, and then it doesn't fit tight against the hose pipe, so they end up grouting the annular space between the liner and the hose pipe to kind of create somewhat of a structural repair. I've never seen spiral wound used in Alaska. I think that at some time it probably will be used here, you know, considering the fact that a lot of the culverts in Alaska are getting older and they're deteriorating. There's a high probability that you could end up seeing this technology come to our state. I've never personally worked with it, but I think it has a lot of possibilities. Coatings is kind of another offshoot of trenchless technology. It's basically, and I'm guessing that a lot of you guys in the room have probably done some of this, where you're coating the inside of a structure that's maybe a part of a project. There's a lot of different types of coatings. They're non-structural for the most part. You've got cement, epoxy, polyurethane. Some of them are sprayed on, some of them are hand applied. Shotcrete is a system that I do know that there's tools up here in Alaska for doing that. We don't see it very often. And coating, one of the biggest reasons for coating is to corrosion-proof the inside of a concrete structure that may have been attacked from gases or something else. Grouting is another aspect of trenchless work that is a term that's used for a lot of different things that happen in the industry. It's a real popular tool, wide variety of different types. And if you look at the pictures here, so the photo on the lower right is a packer that is used to inject grout into a pipe joint and try to seal it up and prevent it from leaking. And in that case, this is an old system that's been around for quite a while. The grout is actually pumped into the soil around the outside of the pipe, and it creates a some sort of kind of like a cement mixture, you might say, and helps to seal the pipe and prevent leaking. It's used quite a grout packing like that is used quite a bit in projects where you're trying to prevent I&I from entering a pipe system. The photo on the lower left is that's a slip lining project where grout was used to fill the annular space between a slip liner pipe and a hose pipe. And that's a cement-based grout. That kind of grout is used a lot in Alaska on slip lining projects, other projects where you need to fill some sort of a gap. You need a flowable product that can fill the gap. In the photo in the upper right, grout's being applied by a worker there who is inside of a manhole, and he's using grout to stop leaks, stop water from coming into the manhole. Basically, he's injecting the grout with a small handheld pump, pushing it into the soil around the outside of the manhole. It solidifies and slows the water down from entering inside the manhole. Just one of the various aspects that you see from using grout in our business. It's been a long time since I've seen an up here, but the other two technologies, grouting the annular space and using grout to stop leaks in manholes, is used all the time. Point repairs is one part of the trenchless industry that's growing. A lot of utilities are buying their own point repair equipment and using it to fix their own lines. It's something that workers can do. And this is basically a short section of cured in place pipe that is used to repair a defect on a pipe that might otherwise be in good shape. And the way that these things work is the crew they'll have a bladder system that's maybe 3 or 4 feet long or whatever length you want to do. They'll put a piece of cured in place liner around it that's still soft, drag it into place, position it over the leak, inflate the bladder, and it basically presses the patch, the little piece of cured in place pipe, against the defect that's in the hose pipe. A camera's involved. Sometimes you have to control the flow when you do that, but it's an inexpensive way to fix a pipe that otherwise is in pretty good shape. And it also prevents digging, in places where you may not want to dig, is, for example, in busy roads or other places where there may be a lot of activity on the ground surface. So I think AWW has their own internal point repair system, if I remember right. Yeah. So very low cost, very popular now with utilities. We see more and more of these coming into the state. Directional drilling. This is a pipe replacement system for installing a new pipe in a new location. You heard me talk a little bit about fixing existing lines. Now we're getting more into installing new pipes, which is a huge part of the trenchless technology industry. Directional drilling really took, when it took off in the 70s, really kind of launched the trenchless industry today. It was a big part of it. And you see directional drilling done in a lot of places, and we see more and more of it in Alaska. This is a surface-launched drilling system that can be guided, and it's steerable. It has a lot of flexibility in terms of where you can put a new pipeline at. There's drilling mud involved in it. The mud is used to remove the cuttings from the hole that they're boring, and it's also used to the drilling mud is used to pack the hole to hold the soil in place as you're drilling underground. There's electronic tracking systems that are used to track where the boring head is going. It's fairly accurate, real popular for water, new water pipes, sewer lines that are at a steep grade. It's not really good for sewer lines that are at flatter grades. You see a lot of electric and telecom wires being installed with directional drilling rigs now. And these rigs come in 3 basic sizes. You got small rigs that are used for like smaller 2, 3, 4-inch diameter conduits that are used in the electrical systems. Medium-sized rigs that are used more for maybe for water mains. And then you have large rigs. The photo on the left is a large picture. That's a picture of a large HCD rig. It's important that the driller that uses this equipment is experienced, and fluid control is also important as well. Without fluid, the drill may not happen. So they need to have mud. Mud needs to be involved in the drill process to make it work. The picture on the right is a photo of the pullback phase of the HDD process. And when they're drilling, they drill a bore path back and forth, enlarge it using reamers. Then eventually the last stage in the drilling process is to pull the product pipe into place. And that's what's happening in the photo on the lower right. For HDD? HDD typically can go up to about 48-inch diameter. Yeah, which, they keep, in the HDD business, they keep installing bigger pipes at longer lengths. But they do some pretty cool stuff with HDD. I mean, and it really shows up like in river crossings and so forth. But for example, in the last 7 or 8 years, where they've got long river crossings that might be like, 6,000 to 8,000 feet long, they're so good that they can drill from both sides and make a connection in the middle of that bore path with two different drill paths. They don't have enough strength in the drill rig to drill from one side of the river to the other because it's too far away. So they have the ability to come and meet in the middle and hook up in the center of the bore path underneath the river. So pretty impressive. Here's some more pictures of the HDD process. The photo on the upper left is HDD being used to put a little 2 or 3-inch pipe in the water storage lagoon at Point Barrow. And so it just shows a lot of the variations of how this technology can be used. They had a water intake that was in the lagoon. They wanted to put an air pipe next to it to be able to blow the air onto the intake to clean it off. And so they drilled into the lagoon. They didn't want to open cut it, make a mess. So they drilled into the lagoon with a conduit, and then they pushed a piece of air pipe inside of it, and that air pipe was positioned so it would point right on the intake. So kind of an interesting facet of how HDD is used. The picture in the lower left is a medium-sized rig. That's about, they vary from a thrust pullback force of about 40,000 pounds to about 100,000 pounds. And then the other picture here is the pullback phase of a pipe that was installed in downtown Anchorage underneath 6th Avenue. So just a lot of different ways of how this technology is used. Pipe bursting is another technology in the trenchless industry. This is a pretty cool one. Basically, you take a hose pipe and pull a new pipe in place using the hose pipe as the conduit for the pulling process. And you're basically pulling a bullet-shaped head through the hose pipe while simultaneously pulling in a product pipe behind it. And a lot of it is just brute force, where you're fracturing the hose pipe with this head, which is, there's a picture of a bursting head in the upper photo here, and then breaking the hose pipe apart and pulling in a new pipe in behind it. There's some limitations. There's some excavations involved with doing this work. You have to go back and reconnect services if it's a water pipe or a sewer pipe, and it can be used in both different types of systems. Bursting, for the most part, is done on hose pipes that can be fractured, like concrete pipes or asbestos cement pipes. There's been some success with bursting steel or ductile iron, but it's not real common. And and one of the things that's interesting for us up here is that one of the pipes that they've never really been able to figure out how to burst is wood stave pipe that has wire wrap around the outside of it. And they tried some different, but basically they want to stay away from that when you talk to the people that supply the bursting equipment. As I said earlier, it can be used for both sewer and water. The benefit here is that you can upsize the pipe, and that's oftentimes why it's used. If you've got a water main, for example, that's too small and you want to burst it, you can burst it and put in a larger size pipe. And that's one of the bigger benefits. It's used a lot in sewers and it's used a lot in water applications. In the States, it's pretty popular where the pipes are relatively shallow, like within 4 or 5 feet of the surface. And the excavations to dig down and create a bursting pit or tie-in services aren't so extensive. Up here, bursting oftentimes is not cost effective, but we do see it. We do see it here. Auger boring is a boring system that probably a lot of people in this room are familiar with. It's been around a long, long time. It's an old system where the auger boring equipment basically pushes a casing in place and uses an auger to remove the soils as they're pushing the casing forward. It's done a lot under railroads or roadways. Auger boring is awfully limited in length. Maybe 100 to 150 feet might be the kind of length that might be the optimum length. Diameter-wise, auger boring typically can reach up to about 54-inch in diameter. And one of the downsides is you have to dig a pretty large pit. The auger goes in a straight line, casing goes in a straight line. It's really not steerable. What's important is that you get it on the line and grade that you want when you first start, so that it ends up roughly in the place that you want it to be at when it gets to the other side or the end of the bore. There's some limitations with high groundwater or loose soils. Auger boring tends to have problems with those kind of soils. So there is auger boring equipment in Alaska, and it's used quite a bit. And the equipment here has done quite a bit of work over the years. So, pipe ramming is a little bit like auger boring. You're digging a pit to lower the equipment into. It's a non-steerable technique for the most part. You're pushing a casing into place. The difference is that the casing's pushed in with a pneumatic hammer, whereas with auger boring, it's actually pushed in with jacks and it's pushed in by brute force. Pipe ramming is a pretty cool technology. It hasn't been used a lot in Alaska. I really think that it's going to grow here. We'll see more of it. It's oftentimes less expensive than auger boring. And I really think that we'll see more and more of pipe ramming as time goes on here. One advantage is it can be used for pretty large diameters, up to 12 feet. What they do is they just push that casing in with brute force. And then once it's in place, if it makes it from one end to the next, all the way through the bore length, after the pipe is in place, then they go inside of it and they pull the soil out. And depending on the size of it, they'll use different equipment to remove the soil. And one advantage is, that you really minimize the potential for creating any voids or anything like that in front of the pipe ram. It's also pretty successful with pretty, tough soils that might have a lot of rock in them. Essentially, they just they'll beat this casing right through rock or any kind of, marginal or tough soil. If you run into an obstruction when you're ramming, what you'll do is you'll remove the ramming equipment from the casing and you'll take the soils out of the casing, go inside of it, and if there's an obstruction, they'll go in there and physically remove it. Let's say, for example, they run into a wooden piling or something that they can't get through. So you do have the opportunity to remove obstructions if you have to in the middle of your pipe ram process. Pipe ramming typically can be done faster than auger boring. In the States, when the two bid against each other, you see pipe ramming winning a lot of different projects. So I think we will see more of this in Alaska as time goes on. Microtunneling is pretty cool technology. I don't know that there's ever been any microtunneling done here. It's very popular in the lower 48, especially for like long, deep, large diameter pipelines, where you've seen big cities where they're trying to go from one point to the next. They'll use microtunneling to basically tunnel underneath the city, oftentimes at 50 or 60 feet below the surface, and create a pathway basically for maybe a large diameter sewer or a large diameter water pipe. It comes in a lot of different sizes. You can see from the photo in the upper right there, these are a bunch of different microtunneling rigs all lined up next to each other. And it's controlled remotely, different than tunneling where you might have a person in there. Non-entry. The cuttings are removed either with a slurry or some other type of process. And as the tunneling machine goes through a little bit like pipe bursting, so they tunnel along, the casing is going behind it, and they're building a pipeline as they're drilling along. One of the biggest advantages is guided, so you can keep it on grade or where you want it to be. They sometimes do got great accuracy, and with microtunneling, you can drill through almost any type of soils. And I've seen projects where, like I said earlier, microtunneling is often used for deep, large diameter pipelines in cities where they have a lot of congestion on the ground surface. But I also saw a presentation where they used it on the East Coast in an older colonial aged community. Where there was a lot of archaeological items on the ground surface. They didn't want to dig a big trench through the middle of town to put a pipeline in, and they used microtunneling to put in a large diameter pipe that was only 12 feet below the ground surface, real close. So, it's an expensive drilling process, and so they were willing to pay that expense versus the disruption on the ground surface. I was surprised that they could drill that close to the surface and not cause a problem with voids or hitting obstructions or things like that. So this is a technology that's used a lot on the West Coast, for example, and I think that at some point we will begin to see microtunneling in Alaska. Pilot tube microtunneling sounds the same. It's like the question you asked about CIPP. But so this is more of a smaller diameter system. This is a laser guided boring limited to about a 500-foot length. And for small diameter pipes and pits, you need to have ideal soil conditions to use PTMT. very accurate, popular for on-grade sewers, especially in the States where you're going from you want to put a pipe in from one point to the next in the middle of a city, for example. The tooling, the equipment itself, it doesn't take a large pit in some cases. The picture on the lower right shows a pilot tube micro tunneling equipment that fits about in the size of a trench box, 20-foot long trench box. But in the upper corner is a picture of a micro tunneling machine that fits inside of an 8-foot diameter casing. So it's used a lot, like in cities where you don't have a lot of room to maneuver. They will construct a vertical case on, drop in this guided tunneling equipment, you know, and they'll bore whatever distance they need to go. Usually it's 300 to 500 feet. And when they're doing this, they've got pieces, the augers and the casings are all very short. So they put them in short segments, you know, one by one as they move ahead and move back. And it's real popular for on-grade sewers or pipes that need to be, you know, in a precise location. It's also very, very popular in places where you might have a lot of utilities. You want to make sure that when you're going from one point to the next, that you stay in the position where you want to be so you don't run into something else. The picture on the lower left shows a close-up of this other rig that's in the other photo. And you can see there's the operator sitting there. He's running the controls, and he's got a TV camera on his left. And that TV camera's got the laser in the image. So he can guide himself along as he's going along and boring along through his bore path. So that's kind of how they do that. They can go 400 or 500 feet and hit within an inch of their target. So real. Yes, sir. Oh, pipe diameter. Pilot tube micro tunneling generally used to be, it couldn't go any bigger than about 16, 18 inches, but I think they're doing it up to 24 inch now. Yeah.
And how small?
How small? I want to say 8 inch. Yeah, I don't really know the exact answer to that question, to tell you the truth. Yeah, on the small size for PTMT. Piercing is basically a pneumatic hammer that drives itself through the soil, unguided, and real popular in short electrical and telecom wires. It's in short, I want to say that maybe, you know, less than 30 to 40 feet. This equipment is used in Alaska. I've never personally worked with it myself, but and these hammers come in a bunch of various sizes, and they're driven by air, and so they just pound their way through the soil. They're not pushed with any kind of mechanical equipment. They just walk through the soil themselves, and they're non-steerable, and it's pretty crazy, but you don't really know all the time where they're going to end up at. And we've heard some funny stories about the piercing tool popping up out of the ground surface 20 feet from where it was supposed to go. And I think in the States, you know, or maybe in places where you have fine-grained soils, you don't have a lot of obstructions like gravel and so forth, like we might have here, it probably is a lot more successful, but it is used here. And it's just one part of this industry that anyway is adaptable to this industry, the electrical and telecom industry. You can see the picture in the lower right here. You know, that's the piercing tool coming into a pit, and of course there's other utilities in the pit too, right? So they obviously wanted to make sure they opened that pit up to make sure when the tool came through there, they didn't run into that pipe that's crossing through there. A real interesting type of method for installing new pipes or new wires in the ground. Another facet of the trenchless business is condition assessment. And this is really about if you've got a pipeline, you're trying to figure out what's wrong with it before you go to fix it. And there are just a lot of great tools nowadays for doing condition assessment, especially with the way the electronics are in, you know, being improved on a, you know, all the time. It's important because engineers, to make a decision on how to fix something, they want to know what the problem is. And so cameras are probably the most used tool in condition assessment. These are images here of different pipes with different problems. The one in the upper photo is a concrete pipe that's got interior corrosion that a camera observed. The photo on the lower right is a wood stave pipe that had some deterioration of the wood staves themselves. You can see the wire wrap in the picture there. And then the picture on the lower left is a ductile iron pipe that's got exterior corrosion that that can be detected with a couple of different types of tools. And I've got a few more slides on this that I'll show you that explain a little bit more about assessment. So some of the tools for sewer condition assessment, you've got mainline cameras, you've got robotic cameras. They've got ways now to look at the sewer services. The camera that's in the lower left-hand picture has actually has two cameras mounted on it. That's a lateral launch camera, they call that. So that's a piece of equipment that walks down a sewer pipe, and then when it gets to the service connection, it has a second camera on it that can crawl up the service connection from inside the sewer main. And so you're doing all this without having to dig a hole in the ground. All the access is all through a manhole. And these lateral cameras have really evolved in the last few years. The photo that you see here is one of the earlier models. That's probably 10 or 12 years ago. Nowadays, you've got sonar, you've got laser profiling, you can map the interior of a pipe. Just a lot of really neat tools available now to figure out what kind of a problem you might have with a pipeline. The picture on the right is a handheld downhole camera for looking at pipes from the ground surface. That's a zoom camera, they call that, a downhole zoom camera that can look up a pipe anywhere from 50 to 100 feet, depending on the diameter and the condition of it. In Anchorage, we're seeing more and more of these downhole cameras, and also some small communities are starting to buy them too. Real useful tool, especially today in today's world when you have rules about climbing inside of manholes and so forth that prevent you from doing that very easily. Here's just some pictures, some of the assessment tools. The picture on the lower right is a robotic camera. That was a red zone camera, and that thing crawls on its own up a pipeline with nothing attached to it except for a small piece of string. And it records the inside of the pipe as it travels along, and it can sense manholes, and it can sense when to stop. And what it'll do is it'll, like on a sewer pipe, for example, it'll crawl up a sewer pipe until it gets to the point where it gets to the next manhole. It'll automatically stop and then back up to the manhole where it was first set down. And so it's truly a robotic piece of equipment, and doesn't take a lot of ancillary equipment like a TV truck, for example. The picture in the upper left, which is a full-blown CCTV camera truck. You don't need that kind of a truck to run this robotic camera that's built by Red Zone. The photo in the upper right is a typical CCTV camera. That one's got big wheels on it, so it can be used in storm drain lines and travel through some debris. And then on the lower left, you have a real fancy high zoot camera. That's probably got a sonar attached to it or something else that's used for looking at large diameter lines. And these things just continue to evolve. You get better information, and they become more and more useful. In Alaska, we're seeing cameras now that are in small compact units that can be shipped to the communities off the road system, shipped by air to help them assess what their pipe condition might be. It's an evolving industry. The other thing too I've noticed up here, is that it used to be that there were just a handful of CCTV cameras in the state of Alaska, and now a lot of communities are buying their own cameras. Communities that are off the road system, Kodiak, Ketchikan, are buying their own system so they can assess what kind of shape their pipes are in. Water condition assessment. So there are a lot of new tools for assessing water pipes. Cameras are used. When you're using cameras, oftentimes you have to stop the flow and open the pipe up, but there are cameras nowadays that can access water mains through hydrants when the pipe is still under a live flow condition. You know, so they're developing that stuff all the time. There's pigging, which basically is sending a tool down the pipe to look at the pipe wall. That's the picture on the upper right. They call that a sea snake. It's sent down the pipe basically to measure the pipe wall thickness, which is being done a lot in Alaska on pipes. Well, not a lot, but it's being done in Alaska on pipes where you have corrosion problems, and you want to see, you know, how serious the corrosion is. So the camera, or the picture on the lower left, is a CCTV camera using a water main. The picture on the lower right is a smart ball, which AWW has used that tool off and on over the years, and gives you some information about pipe leaks and so forth. And basically that's just floated down the pipe and you send it through with water flow. There's some non-destructive techniques such as acoustic methods, which send signals through the pipe to assess pipe wall thickness. Non-destructive, you can do that by hooking onto valves and other components on a pipe system to send a signal from one point to the next. Some of the organizations in this industry, and I'm just about done here. NASTT is a real well-known trenchless organization. They have a conference they hold every year in the States. There's a chapter, offshoot of NASTT, that's located in Seattle, in the Seattle area. Another organization that's a lot like NASTT is the UCT. They hold an annual conference. They're kind of based more out of Texas and the southern states. And then you've got NASCO, which is more of a broad association of sewer service companies. These organizations continue to grow and expand, and they're putting out great resources now with like design manuals and technical papers. A lot of stuff's available online from these different groups, you know, to help people understand what's happening in our industry. And then this photo on the right here is actually one of the newer trenchless technologies. This is called Primus line. Pretty cool method. It's a liner that's like a hose that is pulled into place, and then it expands with water. It's non-structural. It's used a lot in long pipes that don't have any service connections or tie-ins to them, and it's really taking off in other parts of the world. One of the biggest advantages of the Primus liner is that it doesn't take a lot of specialized equipment to do the installation work, and of course, but one of the downsides is that the hose that's in there is not structural, so it can collapse if you get high pressures from the outside of it. So anyways, just one of the newer technologies that we see here. So in conclusion, our industry is just continuing to advance and mature. And I've been in it so long, I've seen a lot of that firsthand. It's just amazing what people can come up with when they look hard at trying to find ways to do things. In our work, you want to oftentimes, especially in the drilling side of it, plan for the worst and hope for the best. Because when things go wrong, they can be expensive in the trenchless world, i.e. if they're, you know, drilling and run into a utility by accident, or didn't do their due diligence to find out what was underneath the ground, there can be some catastrophic damages due to that. We oftentimes talk about risk in the trenchless industry, how to manage it and control it. Fixing defective work can be expensive, and we've been seen some projects where liners have gone in that cured too soon before they had a chance to inflate, and they had to find ways to remove them, and oftentimes they're in places where you don't want to dig a hole. And so it's important to do your due diligence ahead of time as much as you can to reduce risk. I often warn people about being careful with unproven techniques. In an industry where you have a lot of research and development and a lot of new ideas, I've seen a lot of them kind of come and go over the years, and it's oftentimes important just to verify that they actually are doing what they say they can do, and maybe it's been used elsewhere. And then with trenchless work, it's not always the most cost-effective solution. Especially in Alaska, where you might look at a technology to fix a problem, but it's not available in our state, and you're talking about mobilizing somebody from the States to come up and do this, who may have the equipment, might be good at it. It can get expensive in a hurry when you're talking about bringing people up with specialized equipment to do one small project here in Alaska. So we always recommend that when you're looking at something new that hasn't been done here before, or is not available here, to check it out and weigh in the cost of doing it versus maybe fixing the problem a different way. So, this photo here on the right, just to close this out, is what's called a top hat installation, where on a sewer main you'll put in a cured in place liner. They'll cut the service out with a robot after the liner's installed, and then sometimes you'll end up with a ragged edge there on this service connection. Maybe the cutter didn't do a good job, or the service connection was poor in the first place, and so they develop these things that look like a hat, which are a little piece of liner that they insert over that service connection, and it goes up into the service and provides a finished, smooth final product. So just another part of the business. So anyways, I'll open it up to questions. Yes, sir?
Seems like an awful lot of this depends real heavily on what your soils are, and knowing that beforehand.
Yeah, so the question was, a lot of this depends on what the soils are, and that's correct. Yeah. In the drilling work, where you're drilling into a new location, it's if you don't know what the soils are, you're making a big guess on what you might run into. And so geotech work's really, really important, especially like in horizontal drilling, for example. As engineers, we do an analysis on whether the drill is going to be feasible or not, and you're looking at a drill path, and you're trying to predict if the drilling mud is going to make it back to the drill rig, or if the pressure is too high, would it pop up to the ground surface? And that's called a hydrofracture analysis, and the soils are a big component of that analysis. And so yes, it's important to get geotech information, good information. Anybody else? Yes, sir?
With the CIPP, the cure in place, NSF 61 for water is going to be a big component. So that's what drives some of the technology there.
So the question is about NSF 61 and how it relates to water CIPP. And you're absolutely correct about that. Yeah, the liners that, or the lining companies that were in the bullet in the water CIPP, those companies all provide liners that are NSF 61 rated. And that was a big deal in the early part of that industry, because the water CIPP liners were developed and used in Canada. And in order for them to move into the US, they had to get NSF 61 certified. And they all went through that process. Yeah. Yes, sir?
I was on a project not long ago where ran a pipe under the road, and they pulled out more material than they needed, so settled. Is that a common occurrence, or is there a way to measure your mud and your soil to get back so you know?
So you were on a drilling project where they created a void during the drilling process. Do you remember what technology they were using?
No, I don't. I didn't get there.
Yeah, and that's a real concern. And there are ways to control that. Maybe they may have had the wrong technology in the first place. But for example, if you're using auger boring, for example, and you're boring underneath the road with auger boring, auger boring really doesn't, it has problems in places where you've got groundwater or running soils, because they'll just start to run into the casing and create a void. And so that may have been part of the problem. But if there are ways, you know, you'll see where places or issues where a contractor may create a void, he has to go back and grout it up, or find ways to stop the soil from entering the casing. So yeah, it's a big concern. And you'll see issues in designs where they'll require you to measure the surface above the bore path before and after the bore and monitor the settlement. And yeah, so horizontal directional drilling under runways, for example, they want to see settlement calculations before you ever drill. Yeah. Anybody else? Good questions. Okay, thank you very much. Yeah. That one, that's auger boring. They actually have a, they have a way to steer that. And what it is, on the very front of the casing, they have little gates that open up.
Oh,
And
technology.
they control them with pneumatic hoses. So that little channel had air hoses in it. Yeah. So like you might have a casing that's big and they have these little deflectors that lift up.
Yeah, it's gonna
Okay, so you just push it this way.
And all it does is create a resistance and tries to steer it one way or the other.
Okay, okay.